It used to be that if you had a few components on a chip, you would do some ad hoc connection, just connect everything to everything. And this paper sort of solidifies the reasons why we need actually to build a network on the chip. A couple papers that look at packet scheduling techniques that are application aware, and one of these we're going to look later during this lecture. And finally, a paper on bufferless networks or minimally buffered networks, which we're going to touch on towards the end of this lecture. And please see the website. We've added some more recommended readings and some readings that I will be mentioning during this lecture. This is today's agenda. We're going to do a very brief terminology review. This is stuff that Owner has already covered. Then we're going to go into some slightly more advanced topics on interconnection networks, some network properties and performance metrics, different ways of managing buffers and flow control, and talk a little bit about router design and different pipelining options that you have in modern routers. And then time permitting, we're going to talk about some research topics for networks on chip. We're going to look at the packet scheduling problem and how some approaches have looked at how different applications behave to change the way that routers schedule their packets. And if we have time, we're also going to talk a little bit about bufferless routing, which I think Owner just touched on in the last lecture. Some basic terminology. You should be familiar with this. If you're not, please stop me, and we'll go over these in more detail. Topology essentially describes how the nodes are connected together in a network. This is essentially the graph that represents the network. Routing defines how packets go from one point to another. And you have different types of routing functions. It can be deterministic static routing. This means the path from A to B is always the same. Or you can have adaptive routing, changes depending on conditions of the network, and so forth. Buffering and flow control refers to managing buffer space inside the network and communicating buffer space availability between neighboring routers. A switch or router is essentially, you can imagine as a black box that has a set of inputs and a set of outputs, and it can connect any of those inputs to any of those outputs. And what we call a channel is a logical connection between two routers. And keep in mind this is a logical connection because later on we're going to talk about techniques on how to make these channels appear as if you had more than one channel, even though you have a single set of physical wires between the routers. Some more terminology. A node, this is a generic term. This can be a switch or an endpoint of the network. This is essentially any addressable thing in the network. Message is it's the logical unit of things that is transferred between the clients in the network. So for instance, if you have a processor, there could be a coherence message. But in the network, that could be split into multiple packets, for instance. And a packet is the unit of transmission inside the network. And these don't have to be the same. They could be, but there's a logical, a logical encapsulation of one. One can contain the other. Packets inside the network are usually split into flits, which are flow control digits. This is essentially the unit at which flow control is managed in the network. And we will go into more detail about different flow control schemes in this lecture. We're going to look now at a few network properties in addition to what you covered in the previous lecture. Yes?
So how big is a packet?
Typical packets for computer architecture purposes are usually correlated with the size of your cache line, because that's usually what you transfer. And you usually have two classes of packets. One is packets that transfer data, so cache lines, and the other ones are control packets. So for instance, you might send an invalidation message, and those are usually very short, and then you might send some cache response, and that usually has the size of a cache line plus the overhead of any control additional data that you want to bundle inside the same message.
What about flits?
Flits usually have the same size as the data path in your network. So if I have two routers and they're connected through 64 links, my flit is usually 64 bits wide. That doesn't have to be that way. There's a sub-classification. So a flit can be divided into fits, which is PHIT, which is the physical unit. Flit is the granularity at which flow control happens. So if I'm sending data to a router and my flit is 64 bits, but my fit is 32 bits, that means I have 32 wires going across, then every two clock cycles, when I pump two 32-bit quantities, I will be transmitting a flit. And that is when the next router is going to tell me, I got I have a new credit for you, for instance, because that's the granularity at which the flow control happens. But you can have narrow wires transmitting over multiple cycles that correspond to a single flit. But typically, a flit is the same as the number of wires you have between two routers.
But it's fixed for a system, or can you send smaller?
Inside within the same chip?
Yes.
So you could use a subset of the wires if you want, but typically in a system it's fixed. So for instance, all routers will be connected with 64 or 128-bit links, or usually more than that because you want the data to be a power of 2 plus control header information or other things that might occupy some side bits. Yeah. But it doesn't change dynamically. You can use a subset of the wires, but you don't change dynamically the amount of wires you have, typically. Oops, sorry, this went into sleep. I hope this doesn't break everything. Let's see. Is it back up on your side?
It works up here.
The only thing is it doesn't work there. Is the project. Let me, should I unplug this and plug it back in? The problem is I have a single quarter of my screen displaying now. Okay, almost. Let's see. Okay, let me close this. Does that show on your side? Okay. And just let me enable this thing here. That doesn't allow it to go to sleep. Okay, is everyone clear on the notion of a packet and the notion of flits? That's all you'll need for this lecture. Okay, so we're going to move on to some properties in addition to what you saw up until now. So we can divide networks into regular or irregular, or topologies, in fact. If your network looks like a regular graph, like a mesh or a ring, then it's a regular network. It's not all cases where your communication pattern maps well to that sort of regular graph. So if you have some ad hoc communication of 3 endpoints communicating very densely with a few sensors somewhere else communicating more sparsely, you can build arbitrary graphs and build a network out of that. And in those cases, you might end up with an irregular network. The routing distance is essentially the number of links you have to traverse, or the number of hops going from A to B in a network. And the diameter is the maximum number of hops you might have to traverse to get from A to B. So you take the 2 farthest points in the network, and you see how many hops it takes to get from one to the other. So can anyone tell me what the diameter of this network is here?
6.
That's right, it's 6. So in that case, it would be, for instance, going from this router to this router. And no matter which path you choose, you'll have to do at least 6 hops. So 1, 2, 3, 4, 5, 6. The same goes if you go this way. Okay. And finally, the average distance is if you take all possible pairs of nodes and you look at all of the routing distances between them, take the average of that, and you get the average distance of a network. Okay. Another type of classification is if the network is direct or indirect. In direct networks, the endpoints of the network, so the clients or the addressable units of the network, sit inside the network. In indirect, they sit outside, so on the edges of the network. So what do you think this network would be? Would this be direct or indirect?
Indirect.
Indirect, that's right. So this is indirect because you have intermediate nodes in the network that don't have any endpoints attached to them. And the endpoint sits on the edge of the network. If I populated these routers as well with endpoints, then this would be a direct topology. And similarly, this is a direct topology because every router that you add, you also add an endpoint. So the endpoints and the network are mixed in the same area. Okay, so this is an important metric. It's called bisection bandwidth. This is often used to characterize a network in terms of its potential performance, but there's a caveat that comes with this. and essentially refers to if I look at the network as a graph, and I try to split that graph into two equal parts in such a way that the links between the two parts are the minimum number of links, then the bandwidth that can go through those links is the bisection bandwidth of the network. So going back to the example of a mesh here, just to make sure you understood this, let's assume that each one of these links is 1 gigabit per second. What would you say is the bisection bandwidth of that network? It's 4. So in this case, it's pretty obvious. You know, you can cut it this way, you can cut it this way. But if you're going to have 8 on one side and 8 on the other side, and you want to cut the minimum number of links, you're going to end up cutting 4 links. And if each one is 1 gigabit per second, you have 4 gigabits of bisection bandwidth. Okay. So just be careful that this can be a little bit misleading for a number of reasons. One is that it's a high bisection bandwidth doesn't always mean that a network, or if you have two networks and one of them has a higher bisection bandwidth, that doesn't always mean that the higher bisection one is going to outperform the lower bisection one, because you might have some application-specific pattern that makes the bisection bandwidth not matter that much. For instance, in the case of a mesh, if I have this half of the endpoints talking to this half of the endpoints, then yes, this will become the bottleneck. If I have just neighbor traffic, so every endpoint just talks with its neighbor, then this won't be the bottleneck. This topology is fine. You don't need something that offers you more bisection bandwidth, like a crossbar. So keep that in mind. And one more thing that I didn't mention. When you look at bisection bandwidth, the way we looked at it in a static way, we said, OK, this might have 4 gigabits of bandwidth across these 4 links. That doesn't mean that the network will be able to use all those 4 gigabits, because you don't always make perfectly optimal scheduling decisions here. Some cycles get lost across these links. So usually, that's a top bound, the bisection bound. You usually get less than that, depending on the traffic pattern, the number of collisions, how many virtual channels you have, and so forth. OK, and the last property we're going to look at is if a network is blocking versus non-blocking. This can be a little bit tricky to get, so we're also going to do an example. So what this says is, if I have a network that's connecting, let's say, 8 endpoints with another set of 8 endpoints, and you give me any permutation of these endpoints connected together, if the network can connect them and allow them to talk at full speed, then the network is non-blocking. It doesn't block. If it cannot, then it's blocking. But be careful here, because this can get somewhat tricky. And actually, before I go further, let me give you an example with a telephone network. So it used to be that sometimes, I guess several years ago, if you try to call someone, sometimes you would get a message saying that we're sorry, there's no more lines, try again later. And that means that AT&T or the telephone operator didn't have sufficient network capacity to route my call, even though the other person might have been idle. And in that case, you have internal contention in the network, and that means that their network is blocking. It can't allow me to talk to someone, even though we're both idle. But be careful, if I'm calling someone and he's already talking with someone else, then it's not the network's fault. Then you have output contention. The network could potentially handle it, so you could have a non-blocking network, but the other person is occupied and he can't pick up the phone. So in that case, you can have a non-blocking network that blocks because the specific traffic pattern is not feasible. There's no way to connect those. Let's look at an example. So first of all, do you recognize what type of topology this is? Close. What's the general family of those topologies? So the general family is the multi-stage logarithmic topologies, and delta is one example. And actually, I didn't expect you to find the specific one, but this happens to be an omega one. And can anyone guess if this is blocking or non-blocking? So usually, you try to find some permutation, some counterexample. And if you find a counterexample, then it's blocking. Otherwise, it's probably not. So here's one thing you can start with. Let's cut to see the bisection bandwidth. So you have 1, 2, 3, 4, 5, 6, 7, 8 links, and 8 things wanting to communicate. So this seems promising. It seems that there's sufficient bisection bandwidth to get everybody across. But this is not, this is a blocking topology, and I'll show you why. So the fact that you have sufficient bisection bandwidth doesn't mean that there's sufficient, I guess, variability in the switching you can make to get the traffic across. So here's an example of a traffic pattern that exposes the blocking nature of this fabric. So let's say those two bottom nodes want to communicate, and you establish a link for them. And then those two green ones also want to communicate. The problem here is that there's no other path to get from here to here. So even these guys, they could be communicating. The network doesn't allow them to communicate because they all have to go through a single link. Some permutations are valid. So there are some connections where all of these guys can be talking to all of these guys. But this specific one is not. So this is a blocking topology. I'll just mention one more distinction, but I won't go into examples for this. There's also the notion of rearrangeable non-blocking. And again, if you think back to the telephone networks, if you had n people talking with n people, and then two sets of people hang up, and they called each other crosswise, then if the fabric can only allow, again, everyone to communicate by changing everyone's connections or changing some connections, then it's rearrangeable non-blocking. That means I could connect them, but I would have to break out to break down all of the connections and reestablish them in a different path. This is not that important, but I left it here for completeness. But this you should keep in mind. If somebody tells you that a fabric is non-blocking, that is a pretty strong property. That means if I have a set of processors and a set of caches, if these two are communicating in a friendly way, in a feasible way, the network is not going to block them. Okay. Now we're going to look at some performance metrics. This is the most common graph you'll see in any paper that has some networking component to it. It's called a low latency graph. You might also see it as offered traffic and packets latency. But the idea is that on the x-axis, you're capturing the load of the network. And this corresponds to how many bits I'm injecting per second or how many packets I'm injecting per second. And on the y-axis, you have latency. And this corresponds to either nanoseconds or a number of cycles. So this is a metric of time. This is a metric of data over time. And the typical shape of these curves looks like this. And low loads, you have a low latency. As the load increases, your latency usually shoots up until it reaches a point where it almost goes vertical. And the point at which it almost goes vertical, we call the saturation throughput of the network. So that means this is as much as the network can give you in terms of throughput. And this point here we call idle latency. So this is, if you have almost nothing going through the network, this is the minimum latency you're going to pay for the packets. Now there's some constraints that define where this curve can live depending on the topology of the network. So there's a minimum latency given by the topology. So for instance, in a mesh, there's some specific paths that you have to go through. And if you have 6 hops between A and B, there's no way you're going to get there in less than 6 hops. But depending on the routing algorithm, it might get a little bit worse. If you're not using minimal routing, and you're not doing those 6 hops, and you're going, doing a detour, it might get a little bit worse. And then if you also add to that the topology, routing, and flow control protocols, other inefficiencies, you get a higher bound for latency. And the same is true for bandwidth or throughput. You have some hard limit by the topology. That would be the bisection bandwidth, for instance, depending on the traffic pattern. But if you have uniform random or something, it could be the bisection bandwidth. Then you have other constraints by their routing. So for instance, if you look at a mesh, if you're doing deterministic XY routing, and is everyone familiar with that? Did owner mention XY routing? Okay, so I'll go really quickly back to just show you this example. Even here. So this is a very common way to route in a mesh. If I want to connect, let's say, these two nodes, there's many ways to get from here to here. I can go like this, I can go like this, I can go like this. What XY routing says is I'll first only go horizontally, and then go vertically. So that only leaves you one path to get there. If I'm only using this one path, I'm sort of losing out because I could also be using this path and getting more bandwidth. But because I'm using X-way routing, I only get a portion of the available throughput. So if you go back to this curve, that could be one of the reasons why you're getting less potential throughput out of your topology, right? And again, flow control or other constraints can reduce that even further. A quick question. If I have a ring network and I only have neighbor traffic, so every node is sending packets to the next node, what do you expect this curve would look like? So this means they keep sending faster and faster and faster. Flat, that's right. It will look flat. So just keep in mind, this is the typical shape, and this is the typical shape you see because people want to study interesting things. They don't want to study neighbor in a ring, which is flat. But it doesn't have to be. You can have topology that can sustain the full load of a given traffic pattern.
Is that average latency?
Yes, this is average latency. And the reason it shoots up is, so one question that comes up sometimes is, why does this shoot up to infinity? And the buffering of the network is finite. Why isn't there a cap? If I wait on all of the buffers the maximum time, I should be done in 800 nanoseconds no matter what. Well, that's not the proper way to measure this because you want something that it's not dependent on the buffering that you have in the network, because a packet, if it can't even get injected into the network, is waiting somewhere else. So the way these are generated is you usually assume infinite buffering right at the edges of the network, and you timestamp the packets as they go into those infinite buffers, and you also count the time they waited in those infinite buffers before going into the finite buffers into the network, and that's why these shoot up. Yes?
So you talk about X-way routings. You don't route even when the link is busy? How does it?
So that is a good question. We're going to see what happens if there's a conflict. So if the link is busy, and I also want to use the link, what options do I have? We're going to look at two ways to deal with that. So I'll give you a hint. One way is to store the thing that I want to send until the link is not busy anymore and send it then. But there's other things we can do as well. Okay, latency is another important metric. This is, I guess, the basic formula for getting latency. There's many variants of this, but what this just tells you is d is the distance. In this case, it says Manhattan distance because that is the distance in a mesh. If you go horizontally or vertically, or any minimal path you take is always this distance. L is the packet size, how many data elements I have to send. B is the channel bandwidth, so both of these are in bits. And V is the propagation velocity through the network. So this is an ideal scenario. Well, essentially, think of it as like this. If I have to send a packet through the network, then the latency I'm going to pay is the initial latency for the head of the packet, the beginning of the packet, to get to the other side, to its destination. And then I also need to pay the latency for draining the remaining of the packet, right? So this is the propagation until the beginning of the packet gets to its destination. And then I pay this extra time to drain the packet, which is packet size dependent. So if I have a big packet, I'm going to wait a lot of time to get it out of the network. In reality, you also have other things. It's not ideal. You have some time that you might spend in the router, just going through router structures and updating things. And you might also have time that you spend in conflicts, which is exactly what you asked. If the link is busy, I'll have to wait. So that is what this captures. It's a time that I'm just contending with other people to use the links, for instance, or the buffers. OK, let's do a quick review of what we saw so far. So what do you think is the first topology there? It's a crossbar, that's right. The second we already covered. It's a multi-stage logarithmic type of network. And the fourth one is a mesh. These we already kind of saw, indirect, multi-stage logarithmic direct for the mesh. Is a crossbar blocking or non-blocking? What do you say? No, it's non-blocking because it can connect any possible permutation. And this is a point where you have to be careful because it might seem that it cannot, but it's not necessarily the network's fault. So let's say you had node 1 and 2, both trying to talk to node 0. It's not the network's fault that those connections cannot be made. It's node 0's fault because he can only listen to one guy at any point in time. So always make sure when you're trying to figure out if the topology is blocking or non-blocking that you're looking at a feasible traffic pattern, meaning that you're not oversubscribing some of the outputs of the network. If you give me any valid permutation from these guys to these guys, this network can switch it. So multi-stage logarithmic, this particular one is blocking, but they're not all blocking. And it depends sometimes on the number of stages you have. If you add more stages, so you have more path diversity, a blocking topology can become non-blocking with one more additional step, for instance. So in the example before, we saw that two connections had to share this link, but if I had a few more links, maybe that wouldn't be the case because I could go from up then down. And what about the mesh? Is that blocking or non-blocking? No, it's blocking. Well, so in this case, non-something is good, so it's not bad. So the mesh is blocking. Let's see an example. Why is this blocking? If you have a mirror here, and you have every endpoint on this side talking to its equivalent on this side, that's a feasible traffic pattern. Everyone has an outgoing bandwidth of 1 and an incoming bandwidth of 1. So that should be able to work. But because you only have 4 links here, it won't. You need 8 connections going across, and you have 4 links. So this is blocking. Oops, that was, well, anyway. So the cost of the crossbar is n squared, where n is the number of endpoints. So if I add one more endpoint, I need to have a new row and a new column of connections. So I'm paying n squared. What about the multi-stage logarithmic network? Can anyone give me just an estimate, ballpark figure? So what do you think that the cost would be of adding n nodes in that network? So it's kind of given away by the name. So it's almost log n. It's n log n. And the reason it's n log n, so the logarithmic refers to the number of stages here. You have order n things times log n stages. So it's n log n. And if you look at this, each stage, the number of routers in each stage is proportional to the number of endpoints. But the number of stages is logarithmic in the number of routers you have. And for the mesh, this should be easy. So as I scale the number of endpoints, what does it cost? I'm sorry? Somebody mentioned it. So let's say you're adding one more endpoint. What else do you need to add along with an endpoint? A router. So it's as many endpoints as you add, that's as much as you pay. You can keep adding without exploding the cost. So the crossbar has a fixed latency. Anywhere you want to go, it's one hop away. Multi-stage logarithmic is log n, as this is actually what the name refers to. You can get there in log n steps because they have log n stages. And what about the mesh? If I keep on adding more nodes, how will my latency be affected? And it's square root of n. Because you're growing a square, but if you were growing a line, like a ring, it would be n. But now because you're growing in a square, you don't always get that far away that quickly.
Could you explain why the crossbar is non-blocking?
Yes. So to see if it's blocking, you need to see if there's any feasible traffic pattern. So does that make sense, that part of the feasible traffic pattern?
I think so.
So the feasible traffic pattern means that I take some permutation of the inputs and outputs and hook them together. But I can't have two talking to one. It has to be a one-to-one mapping. Otherwise, they won't be able to communicate because they themselves can handle more than one connection. So I have some points here, some points here. I wire them together in some arbitrary way. And then I see if this topology can allow that to go through. Now, do I have a pointing stick or something? I can't reach that high. So in this example, any permutation you give me, I can route through this crossbar. So let's say I had 0 talking to 1, 1 to 2, 2 to 3, and 3 to 0. So 0 could go like this, 1 like this, 2 like this, and then 3 could go through this vertical link. And there wouldn't be any conflicts because every one of these, you have n squared connections, and you just pick n of those that you want to turn on. And as long as there's no data flowing on the same row and same column, so you have a guarantee that only 0 is using this row, and only 0 output is listening on this column. So as long as you don't have any conflicts like that, so for instance, as long as not both 0 and 2 are trying to talk to 2, which means they would conflict in this column, then the traffic can go through. And that's why it's non-blocking. Does that make sense?
Yep.
Can you explain why the latency in the crossfires or?
Yes. So these elements here are just connections. They're not routers. So if I want to go to 1, this is not a hop. I don't go 1, 2, 3. This is a wire. This just shows potential switches where you can just connect two things together. So anywhere I go becomes a single wire. It's a single hop. Yeah, I think in the last lecture, owner showed a picture of a crossbar that had, what was it? Tri-state buffers, I think. And you should think of it like that. I can make a connection at any one of these points, a direct connection, so just putting two wires together. So I can make a wire exist between any input and any output. So I can get in one hop to any one of these endpoints. OK, we're going to talk about buffering and flow control now. First, a bit of review on circuit versus packet switching. And I think owner already touched on this, so I'll go over this quickly. In circuit switching, you set up the full path before you start communicating. This is kind of similar to a telephone network. You first dial. Once the connection is established, you can talk as much as you want, uninterrupted. You have the full bandwidth of the line. You get fast connection guarantee on the line that you established, but you have to do the setting up and bringing down. And you're occupying the whole links. Even if you're not using the whole thing, nobody else can use it because it's dedicated to you. Packet switching is more like the USPS style of sending things. You put a label on it, you give it to them. They take care of how it's going to end up to its destination, and you don't know beforehand how it's going to happen. You don't pre-establish a specific path. You just pass it on, and then opportunistically it makes progress as it can. The good thing with this is anytime you find an opportunity to use a link, you can go ahead. You can try to use it. The bad thing is it's potentially slower, and you might have conflicts. All the packages might not fit on the truck, so you might have to wait for the next truck. Advantage is that you don't have to do the setup and bring time. When you go to the post office, you don't have to notify the receiver that you're going to send them something. You just give it to the post office, and eventually we'll get there. The other alternative is packet switch networks, and we're going to take a brief look at typical packet format. So packets usually consist of a header. This can be, for instance, a single flit, head flit, that can contain routing and control information. And by the way, do you have any idea why we want to have this information at the head of the packet? So why do we want to have, for instance, the routing information at the beginning of the packet? Not exactly. That could be for another scenario, but specifically for the routing information, one advantage is that If I'm a receiving router and I start getting a packet and I see the header, I can directly start forwarding it to the next router because I know where it's going. If I had to wait all the way to get the last part of the packet to see where the packet is going, I would need to accumulate it in my buffer space and then look, oh, it's going there, and then start sending it. So I would be losing time. So you want to have usually routing at the front for this practical reason. Then you have the payload or the body. This is the data, the interesting part of the packet. And finally, you might have a tail section of a packet. And for instance, this could have, again, control information, for instance, an error code. And any ideas why the error code would be at the end of the packet?
Generally, you perform some sort of operation on the information that's being sent through one error code. So
That's right.
Like you have to wait for everything to go.
Exactly.
Before you actually have it.
That's right. So essentially, as the packet is going through the router, you want to generate that information. And if you already started forwarding the head of the packet, you want to put it at the end. Because if you had to put it at the beginning, you would have to wait to see the whole packet, compute it, and then put it in the beginning, and then send it. So there's the stuff that goes here and here is usually for such practical reasons. So now we're going to go to the question that you asked about the links and what happens if a link is busy. So let's say you have one packet coming from the north and one coming from the south. They both want to go left here. What options do I have? I have a single link. I have two packets both wanting to use that link. What kind of options do you think I would have there? What does TCP do? If there's a lot of packets and it can't handle them?
Send them to somebody else.
No, you're biased from what owner told you about Bufferless last time. So in TCP, if you get a packet that you can't handle, you don't usually send it to someone else. What do? No, you just drop it. You don't accept it. You forget about it, right? So that's the simplest thing you can do. If a packet arrives, I don't have any buffer space, I can't handle it, I forget it, and then it's the sender's responsibility or some higher level protocol to retransmit. The other options were both mentioned. So the other ones, you can buffer it. If you have space and you've made sure that there is space when the packet arrived, you can put it in a buffer and have it wait. And third option is what you mentioned, send it somewhere else, deflection. So those are the three options. We are going to look mostly at buffer networks. And for small networks or on-chip networks that are mostly relevant to this class, you do buffered networks. Because you have a control environment, and it doesn't make sense to waste resources by dropping packets and getting the overhead of retransmissions and that kind of stuff. We're also going to talk, if we have time, about bufferless routing, which does what you mentioned, just shoots the packet somewhere else. And it expects that at some point it's going to reach its destination. So we're not going to look that much into circuit switching. We're mostly going to focus on these three packet-based techniques for flow control: store and forward, virtual cut-through, and wormhole. And first, let's just quickly look again at circuit switching. This is just for completeness. As we mentioned here, you don't have a need for buffering because before I start sending, I've guaranteed that I have the whole path ahead of me open to send my packets. And you don't have any contention. I have guaranteed that path. There's no other packet coming in my way as I'm sending. Another advantage is that because I have the whole link, I can start sending, and I can stop whenever I want. There's no limit as to how big of a packet I can send. I can just keep on sending. These we mentioned already. You have, you might not be using the full link. Nobody else can use it. And you have this overhead of setting up and tearing down the channel. Now, onto packet-based flow control techniques. So this is the simplest one. It's called store and forward. And it's exactly what the phrase is saying. Essentially, if I'm sending a packet from a source to a destination node, each hop of the way, I send the entire packet. So I first send the entire packet to the neighbor node, then to the neighbor router, and finally the whole thing to the final destination. Now, the problem here is that you have high per packet latency, because I have to wait for all the cycles to get the packet here, and for all the cycles to get the packet here, and for all the cycles to the packet to get there. And you also need enough buffer space to store the entire packet on this router, and this router, and this router, and so forth. Does anyone have any ideas as to what I could do that's better than this? What do you mean by out of order?
Let's say you have 4 flits, right? And all of those flits have some kind of, I don't know, matching address and send them on different routes. And
That's a good idea.
Recompute them.
So that is a good idea. It's kind of an advanced thing you would do. So what's your name?
Tom.
Okay, so what Tom is saying is you can send some parts of the packet this way, maybe some parts of the packet this way. So this is called multipath routing. We're not going to look at that, but that is a possibility. That becomes complex on the receiving side because you have to reassemble it, and you might have. I'm looking for something simpler, and I guess it's somewhat related to that. You don't have to wait for the whole packet to get here to start forwarding. So if this router already knows that the next router has enough space for the full packet, by the time he gets the first flit, he can start sending it forward, right? So this is what we call cut-through flow control. And it's exactly that. You're cutting through. Instead of waiting, you just keep on going. As soon as the header received, so let's look at this. Oops. Actually, well, now you saw it. So the main advantage here is the latency. I won't hit the next. What's a disadvantage, or what's a problem we didn't solve with this? So this guy knows that this guy has enough router space, and this router knows that this router has enough buffer space. So we can start forwarding parts of the packet before the entire packet is stored in the next router. But what kind of disadvantage do we still have?
Does it mean that, I'm not sure if this is true or not, but does it mean the other 2 routers can't do anything while it's waiting for the information to get to it?
It's close to that. So it is that the other routers still need to have the full buffer space. So when this guy starts sending, this router starts sending to the neighboring router, he's sending because he knows that this router has enough buffer space. And the fact that he has enough buffer space means that you still need to potentially store the full packet there. Ideally, you won't have to, but if you find a conflict later on, the whole packet will accumulate in an intermediate router. So this is what this looks like. You start sending the packet. Before the whole packet is at the second router, you can start forwarding to the third and so forth until it gets to its destination. If packets are large, you need big buffers still, like you did with the original flow control scheme.
Why you need the whole buffer space to fit the whole packet?
So what are you suggesting?
I mean, you could just, even if it has, like, say, space for half the packet, why is that a problem? It might just jump to the next router anyway before it fills up.
So I think your suggestion is very close to what we're going to see in the next slide, which is exactly, it's the same thinking, but there's some complication there. So let's say you start transmitting. And actually, I'll go back to the animation. And I'm stuck in this state. And I didn't check that if I checked beforehand that this guy has enough buffer space, I would be able to drain this into him. If this guy doesn't have enough buffer space, and he suddenly tells me, you know what, we have to stop this transmission, I don't have enough buffer space, then I would be stuck in this weird state where a single packet is at 2 different routers in the network. So this is not something that is impossible, but it sort of breaks the abstraction that if I start sending, I can contiguously in one shot finish with what I'm sending. But this is the next technique we're going to see, and it's called the wormhole routing, wormhole flow control. And it's exactly that idea. And it says, well, why don't we let parts of the packet, as they're going through the network, wait a few cycles at different parts of the network. This seems to make the best use of the buffer space, because I don't need to have enough buffer space to store the entire packet, especially if you have big packets. These buffers could grow big. I just need at least a couple of buffer entries to store the part of the packet that's currently going through my particular router. Can you see any issue? Let's say I have this packet, the head has reached here, the tail is still here. What kind of problems could this cause in the network? I might not be the only packet going through the network. So what kind of issue could you have there?
Is it possible to have deadlocks?
It's not that much a matter of deadlock at this point. It's a matter of you're occupying resources across multiple places. So if I'm occupying some buffering here, and some buffering here, and some buffering here, I potentially am not allowing stuff to flow through this router. And if this guy's stuck across a big part of the network, then I could be blocking many routers. It could be tied to deadlock. Actually, I haven't given enough thought to that, but we're going to touch on that a little bit later. So I'll show you an example of an even sort of worse problem. First of all, we already kind of covered this. So going from the original solution, the packet just goes in its entirety from one router to the next. What are the advantages of doing wormhole routing? So one we already mentioned for cut-through, what was the advantage there? Reduced latency, exactly. And the second advantage, we just talked about that, it's the buffer space, right? You don't need that much buffer space. This is what we just mentioned, the limitation occupies buffer space across multiple routers. And this is the most important part. This is a very common problem in networks. It's called head-of-line blocking. So you start running into head-of-line blocking problems, and we're going to look at an example to show you what that means. Let's say you have a small switch, 2 by 2, 2 inputs, 2 outputs. You have a set of packets, and the number in these packets corresponds to the output they're headed to. So input 1 has packets for output 1, 2, and 1. Input 2 has packets destined to 1, 2, and 2. And they're waiting in these queues. The problem is that the packets at the head of the packet, at the head of the queues, they both want to go to output 1. Since output 1 can only accept one packet at a time, it's going to pick one of the two, let's say the top one, and then the second one is not making progress. The packet behind the first packet here could be making progress because output 2 is idle. The packet is just sitting here, and it's not making progress because this guy is blocking it. But this guy isn't making progress either because it happened that the other packet destined to 1 is making progress. So does this make sense? This is a very central problem, and many of the optimization techniques and networks have to do with solving this sort of problem.
So why is it specific to one? Why is that specific to one port?
You mean to one port?
To one port flow control? Is it a specific disadvantage to one port?
Oh, it is tied to that. It's not. It's a more general problem. But if you start having small parts of your packet floating around the network, there is a bigger chance that they'll be blocking someone else. Because if I'm forwarding packets in their entirety, then by the time I start draining, a large chunk of ones, they're all going to be out. If I'm doing wormhole routing, you might have this interleaving of different packets in different queues, and there's a higher chance that you'll get head-of-line blocking. But it's a general problem. You could also get it with the original scheme. If I had multiple ones, and then multiple 2s back here, I would still have the same problem. But here it's exposed more. You have these small segments. This is another picture showing, in a bigger network what this would look like. So let's say you have some blue packets, flits, wanting to go to this node, and some red ones that want to go to this node. And we're doing XY routing, so we have to go like this and this. And this intermediate router is already blocked by other stuff that was headed to some other place. So the problem that I have here is the blue ones start making progress. The lower router fills up. And then this router also fills up. And then the red ones cannot make progress because they're blocked by the blue ones. But there's no real reason why they couldn't be making progress. The red one is ready to receive. It's the blue ones blocking them. Can you think of any solution to this problem? What would you do? How would you change how we're organizing flits in these routers to improve this situation? So going back to this picture, it seems like in each input, I'm taking all types of packets and putting them in a single queue. What would you do to fix that?
Could you either reroute or enable your routers to do simultaneously routing?
How would you do the simultaneous routing? So the router only sees what's at the beginning of the queue. He can't see what's back here.
So that is saying, like the first from the same packet only exists in one queue.
Exactly. So that's the source of the problem. And to solve that, you need to separate packets into separate queues per input. So even though they're coming from the same input, I don't put all of them in the same input queue. I put them in different queues. And that's the idea of having virtual channel buffers. And they call them virtual channel. You'll see why. Actually, this is one of the first papers that looked at the effects of head-of-line blocking and how much they can limit your potential throughput. This is the picture showing a single buffer per input. So each one of these, and then you have a single buffer. And then the evolution of this says, OK, let's not have a single buffer, because that's causing this head-of-line blocking thing we don't want. Let's split it into two, or more, but even two can kind of fix the problem. And this is also a seminal paper, Bill Daly. You can take a look at it. It's called Virtual Channel Flow Control. It introduces this idea of splitting traffic. This is in more detail how you could split, the same number of entries in terms of buffer space, but organized in a different manner. And here's an example. So now we have each router with two queues. And here it happened to be that the red ones were placed in one queue, the blue ones in another one. This guy's still blocked. He does have two queues, but there's still too much stuff, and he can't handle it yet. So looking at the same example, the blue ones still get stuck there, but now there's another queue that the red ones can make progress through. So the red ones can bypass the blue ones in this case. It's called virtual channels because even though you have one channel here, it gives you sort of the abstraction of having more than one channels because you can bypass other flits. And if you look at the architecture of a modern virtual channel-based router, at the front end, that's usually how you have your virtual channel organized. You have virtual channel buffers. You can have multiple of these. In addition to not having this head-of-line blocking problem, virtual channels also have other uses. One of them is deadlock avoidance, which you already touched on. I think you already touched on some turn schemes for avoiding deadlock with owner in the last lecture. So there was a NISCA paper that if you restrict some specific turns, then you can avoid deadlock. There's similar techniques or other techniques with virtual channels. You can use escape virtual channels. So this means I keep on injecting traffic into my network. If at some point I see that I can't make any other progress, I have this separate set of buffers on a specific virtual channel number, and I switch to that channel of VC. And in that VC, I use some deadlock-free routing algorithm. So I can use arbitrary routing on my common VCs. And if I run into problems, I use the escape VC that guarantees deadlock freedom. So you can drain the network. And then you can also use VCs for isolating traffic and avoiding deadlock at the protocol level. So if I have a network with requests and responses, for instance, for cache message exchanges, you usually don't want to mix them in the same VC because if a response is waiting a request and a request is waiting a response, you have a cyclic dependency. So it's typical that you place requests on VC 0 and responses on VC 1. So you can assign different VCs to different types of traffic and avoid deadlocks. In addition to deadlock, you can also use them for prioritizing different types of traffic classes. If you, for instance, have critical messages or control messages that you want to arrive at their destination sooner and bypass other packets, you can put them in a VC that has a higher priority than another one. OK, so now we're going to move on to the second part of flow control, which has to do with managing the buffer space between routers. So up until now, we're saying, how does a router itself organize its buffer space? Does it have a single queue or does it have multiple queues? Now we're going to look at the problem. There's two routers exchanging packets, and they're trying to figure out how much buffer space there is available to send. We're going to look at 2 schemes in detail. I'm listing 3 here. The most common one is credit-based flow control. That means if I'm sending packets to a downstream router, every time he sends those packets further, he sends me back a token or a credit that signifies or signals that there is additional buffer space in his buffers. So when you reset the system, I start, for instance, with 10 credits, and those correspond to 10 buffer entries on the downstream router. And as I'm sending packets, I reduce the number of credits that I have. If I reach 0, I stop because I know that he doesn't have any more buffer space until he sends me a credit back, and I start replenishing my credits, and I keep on sending. Right? Make sense? All right.
What are these credits exactly?
This is, imagine it's a counter. So imagine I have a wire, a signal that's coming from the downstream router to my router, and I'm maintaining a counter. I start my counter at 10, 16, whatever the number of buffer entries is that he has currently when the system resets. And then as I'm sending flits to him, I reduce my count. And if I reach 0, I know that I shouldn't send more, right? Because that indicates that he doesn't have any buffer space left. And then as he's sending the packets further, so his buffers are emptying up, he's signaling me through this wire to increase my counter. So I know I have more buffer space.
Wire. Is the dedicated wire?
Not always. So you can do out-of-band signaling, which means a dedicated set of out wires. You can do in-band signaling, which means the same wires that carry your packets could also carry your credits. But you need to have some bits flipped to indicate that this is a credit, not a packet. So as the packet arrives, you see, is this a packet or is this a control credit information? But the idea is the same, regardless of which path you use to send it.
You said that when you start a system, one node has, I don't know how many credits. But what happens, for example, if another node is more active and fills in the other one's credits?
So credits are for buffering, in this scenario, for buffering one router ahead. And if I have 10 credits, those 10 credits correspond to 10 buffer entries that are dedicated to me. Yeah, and if I don't use them, then they go wasted. They're not shared. Yeah. There are some more advanced techniques where you can do this. You can either statically partition. So if this buffer space was shared and I had 10 entries, I could give 5 to one router and 5 to another one. In worst case, they would both use the entire thing. But in this instance, just think of it. If I have 10 credits, those correspond to 10 entries that are just for me. Second key scheme is simpler. It's called X-on, X-off flow control. The way to think of this, actually we'll see an example later on. This essentially, imagine there's 2 wires between each router. One of them is called X-on, which is go, and one of them X-off, which is stop. So as a router is receiving packets, if it sees its buffer level or his remaining buffer entry is getting low, he sends an X-off signal. That means the sender has to stop. As he starts getting rid of packets, when he's comfortable, he sends an X-on message. That means the sender can resume sending. So this is very simple. You just have to make sure that because this X-off thing might take a couple cycles to get to him, you need to send it early enough so he stops sending a couple cycles before you fill up, because there might be some packets on the way and you don't want to overfill. And then ACK-NACK flow control. Essentially, this means just keep on sending, and I'll tell you if something goes wrong. So this doesn't give you guarantee of buffer space, but if a packet comes and my buffer is full, I'll send a negative acknowledgement, and then he'll have to resend it later. So we're going to look at credit-based flow control and X-on, X-off in sort of a time graph. Let's say you have 2 nodes, node 1 and node 2, and time is advancing downwards. So node 2, and let's say node 1 has already sent some packets to node 2. Node 2 at some point is ready to send packets further, the ones he received from node 1. So he starts sending those, and at the same time, he sends a credit back to node 1 telling him, hey, I have more space now, something freed up. Node 1 processes that credit. He updates his structures. He does some new scheduling to see what he's going to send next. And then he sends a new flit to node 2. And he also sends a credit to the router behind him to tell him that he has more space, right? So by the time node 2 gets a new flit, he processes this to see if he's going to send another credit back. Now, this is an important time period in a network, and it's called the credit round-trip delay. The reason it's important is because you need to size your buffers to be big enough to cover this delay. Because this is essentially the time it takes for the two to communicate. There's some latency for the signaling to go back and forth. And if you want to have a stream of packets never stop and continuously flow, you have to make your buffers big enough to tolerate these delays in processing and going through, pipeline stages or whatever to get from one end to the other. Okay. So this is the X-on, X-off flow control. This is the simpler scheme. A good way to think of this is sort of, if your buffer is like a barrel, and this is filling up with water, you have two marks on it. You have one that is called X-off and one that is called X-on. So as I'm receiving packets, let's say node 1 is sending packets to node 2. The level of the water is going up. Once I reach the X-off mark, then I have to tell them stop. And there's still some water in the pipe that's still going to flow. But if I told them soon enough to stop, then I have enough space reserved for that extra water that's still trickling towards me. So that is what happened right there. He sent a flit. Node 2 reached this X-off point. He sends back an X-off message. Node 1 still hasn't received it, so he's still sending flits because the X-off takes some time to get there. By the time he gets the X-off message, there's 3 extra flits that were sent, and that's why I need to reserve this buffer space, right? Or 4 in this case. So by that point, node 1 realized that he shouldn't be sending anymore. He just waits. Node 2 eventually starts getting rid of his packets. When the threshold falls down to X-on, so once he starts draining his bucket, when he feels comfortable, he re-enables node 1 by sending an X-on, and the thing goes on. So then he starts sending. Now, you want to send this soon enough, because once you send it, it will take some time for node 1 to start sending you packets again. So you want to have something to do while you're waiting for him to get the message. So you send it early, so you have enough packets to keep you occupied. So I start draining my bucket. I reach the X-on point. I send the X-on message. And I still have some flits in my bucket, so I can still keep on sending these until this guy gets the X-on and sends me more. So the whole thing is you want to keep this occupied. You don't want to be completely full or completely empty. Right? So reviewing what we saw until now, we started with store and forward. You transfer the whole packet from one router to the other. The problem was you have big buffers, long latency. We shrank the buffers and reduced the latency, and we reached the cut-through and wormhole routing technique that we saw, where you start sending, and before you even know if you have enough buffer space further down, you keep on sending. And yeah, that's what it looks like. And then we realized there's still an issue. There's this head-of-line blocking thing that's causing some performance degradation. Let's split our buffers into multiple buffers. So we started organizing flits into virtual channels, and then we could allow packets to bypass other packets. All right. So any questions up to this point? Yes.
So in wormhole routing, how do the non-head flits know it?
So in wormhole routing, there is a contract or an implicit understanding in the network that body flits and tail flits will always follow the head flit. And it's the router's responsibility to keep track of what's going on. So for instance, if I'm a router and I see an 8-flit packet coming in, I see the header flit, and that tells me this is destined to node 8. I forwarded it, but then I need to remember that these remaining 7 flits, even though if they get stuck here, I need to get them to node 7. And the same goes for the downstream router. So you're occupying resources, even though you might be stuck here. The next router still has to remember that there's more of this packet coming, and it needs to get there through that VC. And that's why you're sort of, we said occupying buffer space, and you're also occupying VCs. Because the next router needs to remember, if I get a packet on VC1, oh yeah, I had a header go through that VC, and he was destined to 8. I need to send also the rest of them. And that's state, again, in the router. And so that's the way it works. There's one interesting technique. I don't think we'll have time to get there in bufferless networks, where there it gets even worse. I think Owner mentioned that you have this deflection hot potato routing. What can happen is I start sending the header and maybe the next flit to the downstream routers. I get stuck. And if I don't want to remember anymore, then I can cut the worm and make a new one, so convert an existing flit into a header flit. And then instead of the original sender send one big packet, and I might end up delivering 3 smaller packets because I cut them along the way. But the typical wormhole routing keeps the thing in one packet, and the routers have to remember how to deliver it. We're quickly going to go over some router design and pipelining options. This is just the big picture. You have a set of routers with some processing elements. This could be processors, L2 caches, accelerators, what you want. And the router usually looks like this. It has some input ports. They're organized into virtual channels. That's why you see more than one buffers for each input port. Then you have a switch. That is essentially a crossbar. It's a small set of wires and connections that allow every input to go to any possible output. And you also need some control logic that will select which VC and which packet am I going to serve. In wormhole routing, remember what kind of restrictions I have if there's a packet that's underway. And also control the switch. So who's going to use the switch out of all these packets? And this is, actually, let me go back to here. The next slide just says what this picture is showing. The control logic consists of the routing unit. This means when a packet comes in, I need to figure out which output it has to leave from. So if I get a packet from my south port, I have a table lookup, or I have some arithmetic lookup, or I have some source-based routing, but I have to figure out which port it has to go out from. Then I have my VC allocator. This means I have to choose which one of these buffers am I going to use in the next router. So if I send something through my west port, it's going to arrive at a similar unit like this. And when it comes in, this guy needs to know which VC to use. So this is the VC allocator. The VC allocator communicates with the next router to figure out which VC is available, or which one to pick. And finally, you have the switch allocator, which is what we already mentioned. This controls who is going to use this switch. So I might have reserved, I might have assigned VCs to each one of these packets, but that doesn't mean they can all make progress, because it could be that 3 of my inputs all want to go to east. So I have to make sure that only one of them does, because I can't have 2 packets on the same wire. And this is just the same thing in text. It has a buffering component, does routing computation, it picks between flits, it does the switching, the crossbar thing. And power management is in, this is not a requirement of a router, but this is an interesting optimization to reduce how much power it's burning. One optimization could be similar to what you mentioned. Even though I have wide links, I don't have to use all of them if the load is light in the network. I could use a subset of them, right? And more or less, the pipeline stages in a typical router organization, they correspond to what we saw earlier. So the packet comes in, you have one stage to write it into the buffer. You have another stage to look up its control information and decide which output port it has to go through. And then you tag it. For instance, sort of like in the post office, you sort the packets depending on where they have to go. Then you have to assign virtual channels. And this is assign the virtual channels that the next router is going to use. And you have, for instance, to look at your credits and see which buffers downstream have space. And depending on that, for instance, you can assign a virtual channel to each one of those incoming packets. Then once you know which packets can go through, because there's buffer space ahead, you have to decide which ones will actually traverse the switch in your local router. And there's a cycle that you go through the switch. After you schedule the switch, you go through it. And a link traversal cycle, which is going through the wires between the 2 routers, right? So this is essentially the typical design, has 5 pipeline stages within the router and 1 going through the links. Now, coming back to sort of the question that you asked in the wormhole router, what happens with the rest of the flits? Well, when the head comes in, you have to do all the stages. For the rest of the flits, you essentially remember what you decided for the first flit. So once you assigned an output, the route computation, and a virtual channel for the first flit, the remaining ones have to use the same thing if you want to keep the packet, as one entity. And that's why you only need all 5 stages for the head, but for the rest, you don't need to do these units. They're pre-computed for the rest of the packet. And this is all that this says. This we can go relatively quickly through. So this essentially shows you what kind of dependencies you have. So for instance, to do the switch arbitration, I need to know the routing information because I need to know which outputs this packet wants to use before I tell the switch I need this connection. Because before knowing where it's going to go, there's no way I can tell the switch I need this particular connection, right? So there's some dependencies, and these sort of they restrict what kind of pipeline optimizations we can do. And we'll see a few pipeline optimizations on the next slide. So the first pipeline optimization. This is look-ahead routing. If I'm in a regular mesh network, actually here I can do a picture here. Can the remote students see the kind of? I'll try to talk them through it. A very simple example is a 3x3 mesh. I have a source node. I'm sending from here to here. If I'm doing XY routing, which is what we talked before, I first go horizontal. So I'm going to go like this, and then like this. Starting from this router can do some arithmetic based on the node numbering, or it can just have a table that tells him if you're trying to send to this guy, always send right. This guy knows that he has to send right. Now, this optimization says, why don't we pre-compute also the next hop from this router? So this router can already tag the packet and say, you're going out of my right output, and here's a hint for the next guy, you're still going to go right. So that way when he arrives to this router, the packet, it can already know that it's still going right. And the same here, like this guy can tell the next router, put it in the packet, like have 2 bits to tell a hint as to which direction it's going to go. You're going to go downwards afterwards. So this guy doesn't have to perform a separate cycle, doesn't need to devote a separate cycle for routing computation, can be pre-computed at the stage before. So that way, as you're writing to the buffer, you also get the route computation that was done from the previous router. So you shaved off a cycle. The next optimization you can do is you can opportunistically assign a VC to the packet. So I don't know if there's enough space, but let's say VC2 has enough space, and I tag it with VC2. If it fails, then I still need to, not roll back, but I need to recompute the VC to find a valid one. But if I'm lucky and if there's a light load in the network, the packet might go through in fewer cycles. So I can combine the VC assignment with the switch allocation. And finally, you can also do some bypassing. So if the network is completely idle, I don't really need to go through the buffers. The buffers are there in case there's a conflict. If I knew I didn't have any conflicts, I would do circuit switching without any buffers. So this tries to give you the benefit of circuit switching, no buffers, by bypassing the buffer write stage. So you try to completely go out, and if it happens that you get 2 packets from 2 different inputs, they're trying to use the same output, and you do have a conflict, then you have to buffer one of the 2. All right. Do you guys usually do a break? No? OK. So we're switching now gears, going to some research topics on NOCs. For these, we're going to use the slides from the actual presentations, the conference presentations. I'm going to go through some of the interesting parts and the interesting ideas in those. The first couple of papers, application-aware packet scheduling and RIDEA, have to do with the problem of packet scheduling, and I'll explain what that is. And if we have time, we're going to also touch on bufferless networks, which I think Owner mentioned, at least he mentioned the hot potato stuff. So it's kind of similar to that. All right. So packet scheduling is essentially the problem of picking which packets I'm going to allow to make progress. So just quickly going back to the picture that I showed here, I have a bunch of packets waiting on all of my virtual channels, and then decide which ones am I going to allow to go to the next router. And actually, what would the obvious thing be to do? So you have 20 packets waiting to get sent, and you only have 4 outputs. What would be the simplest thing you would do? If you were a hardware engineer, you worked in isolation on a specific router, what scheme would you use? That's good. So oldest one is one choice. The one that has been waiting the most, and that seems kind of fair. Or an even simpler one would be round robin. I don't care what order they came in. I just get one from here and get one from here and just keep on servicing them. So those are 2 simple techniques, but they have some caveats if you're within a multi-application environment and not all packets have the same importance or have the same criticality. So this defines essentially the problem. You need to prioritize between competing flits. Which input ports do you pick? Which VCs? Which applications if the packets are tagged by application? And this we already mentioned in a round robin, oldest packet. And as you'll see, there's some better policies if you want more performance in a multi-core environment that has many applications running. This is a very generic picture, just a few cores. The network is a black box, and you have connected to it the cores, some slices of an L2 cache, maybe some memory controllers, some accelerator cores, and so forth. And you have different applications running on here, so the traffic that's generated is coming from multiple applications. And I'll skip through this. And now the part that we care about is essentially assigning the VCs. So which packets or which apps do I assign, which packets from which apps do I assign to which VCs, and which packets or flits do I allow to go through the switch. And that's what these papers look at. This is an example. Let's say I have 3 virtual channels in each one of these inputs. So my packets are organized in 3 queues. And these different colors correspond to 8 different applications. And I need to somehow decide which ones I'm going to service. So this is what we already covered. You can do round robin, age-based. The problem with these are they're local decisions. So a router might do round robin, and you might sometimes happen to be a lucky packet that just got in and the round robin scheduler was near your point. The next hop, you might end up being the last one to be serviced. So there is no global coordinated movement of flits. And the other problem is they don't know what these packets correspond to. One of the packets could be some prefetch request. It's not critical, it's just an extra optimization. Another one could be carrying the response to a cache miss and the core is stalled on it. So you want to potentially expose that information to the scheduler. So we're going to look at the first approach, which is application-aware packet scheduling. And the idea here is we tag packets with a metric that is called stall time criticality, STC. And this paper did a study that showed that applications are not uniform in their behavior, and you'll see how much they differ. And it defines the criticality of a packet with respect to network latency. And they call this the STC, the stall time criticality. This metric is essentially the average stall time that is caused by the latency of each packet. So for instance, if the core has sent 10 packets and he was stalled for 100 cycles, then his stall time criticality is 10. So if I'm sending more packets and stalling the same amount of time, then I'm less stall critical because I was still making kind of progress. If I'm sending few packets and waiting a lot, then I'm very critical, stall time critical. My packets should be prioritized. That's the intuition. And we'll see a few reasons why you can have different stall time criticality. This one I should have asked, but the obvious one is memory level parallelism. So I believe you already covered this, right? So this says, if I start servicing a cache miss, there might be a few more memory requests that I can make while I'm waiting on that cache miss, right? And we'll go over these briefly too. So the first one, MLP. This shows with gray is compute time in a core, and those colored boxes are cache requests or memory requests. So let's say this core is computing, it generates 3 requests, and then at this point it needs to wait for this green request to come back to continue computation. When that packet arrives, the green one, it starts computing again, then it needs to wait for the red one, then it needs to wait for the blue one, and so forth. So this application has high MLP, meaning that it can overlap its stalls with the next memory request that it will need. And this is good in terms of tolerating network latency, right? First of all, packet latency is not the same as network stall time because of MLP, because I can overlap these. Now, if we look at an example with low MLP, a similar picture, but let's say I didn't have any other memory requests to send out. I sent the green one. I waited for the green one to finish. Then I got the blue one. I waited for the blue one. If I wait for each one of them individually and I don't have any overlap, then my requests are much more critical because I'm wasting much more time than the guy on the top. So you would expect the guy on the bottom to be more stall time critical than the one on the top. This is a principle called shortest job first. So if you want to reduce your average latency, it usually makes sense if you're scheduling stuff to get the short jobs and get done with them first. But you have to be careful because if you constantly schedule the short jobs first, the longer jobs might starve. So you have to strike a balance there. And you'll see how this approach strikes that balance. I'll go slightly quickly, but just to show an example, light application, which is just generates a few packets. And if the baseline is running alone, then if you do round-robin scheduling, you service one or the other. And I guess the takeaway point from here is if you look at the relative slowdowns, if I prioritize the big guy, the one that has the many jobs, then the guy that has the short job experiences 4 times the network slowdown, and this guy only gets a 1.3x slowdown. But if I prioritize the short job first, then this guy sees only a 1.2x slowdown, and this guy a 1.6. So this guy went 0.3x slower, while this guy got 3.8 difference in the slowdown, a 2.8 different slowdown. So it makes sense to schedule the shortest job first. That's all that is saying. Okay, so yeah, the idea here is you rank the applications based on their STC metric, but to avoid starvation and other problems, you batch the packets, so you guarantee that eventually, the packet will get into the network. I think you already covered the PAR-BS paper, the parallel batch scheduling for memory. Very similar idea, ranking and batching, right? So the ranking, similar to PAR-BS, there is a heuristic that generates these STC numbers. You rank based on those. I won't go into details, but take a look at the paper to see how this mechanism works. There's some ranking intervals. So every 350,000 cycles, you look at the STC of each application, and you sort the applications based on STC. There's the central decision logic that decides, that updates these rankings. Okay. And then the batching component, which I mentioned, which solves that starvation problem. At some point, you have to make progress. So you bundle requests in a batch. And oldest batches are always prioritized over younger ones. So this is sort of the oldest first principle, but at a coarser granularity. So you have some flexibility within the batch. So this is the idea how they use some bits to have a batch ID and a rank ID. And this example here, I think, captures the core of the paper. So this shows you 3 cores injecting packets into the network. You have a red application, a blue one, and a green one. The numbers correspond to when these packets were injected, which cycle. So, and they set the batch length to 3 cycles. So these are one batch, these are the second batch, and these are the third batch. Now, the STC tells us, the STC ranking, that green ones have higher priority than blue ones, have higher priority than red ones, right? So the green ones are the most critical packets. Now let's see 3 different scheduling approaches. So the first one is round robin. You just pick one each cycle. So I picked 5, then 4, 3, 1. You just keep on picking the front packet. So you would end up with an order like that. The next one is age-based. So in age-based, you pick the one that was injected the earliest. So that's the number inside these packets. So then I would first pick 1, and then pick 2, and then pick the other one that came in cycle 2, and so forth. So there's that's the order that came in. Notice that this is not a glitch, but these are not in order necessarily, because you go 3, 5, 4. And that has to do with the order they appeared in the buffer. So the router can't always see all the packets sitting in a buffer. So there might be an older packet sitting behind a younger packet in a buffer that can cause small deviations from a perfect order. So up to this point, each color here indicates the stall cycles that each application has experienced. And what we care here is the average number of stall cycles. We're trying to reduce this to increase the performance. So with round robin, you have 8.3 cycles, stall cycles, average. With the age-based thing, you have 7 average cycles stall time. And now let's look at the stall time criticality. So now essentially we're using the colors to sort these. You first pick 2, which is the most stall time critical. You really have to get this serviced. Then the blue ones, and then all the red ones. And in this case, you have an average packet stall time of 5, which means you can get more performance out of the system. So there is a quantitative comparison in the paper, and you can take a look at that. They compare it against some other scheduling schemes, I think GSF, Global Synchronized Frames. And what this shows is if you look at the system speed up with the stall time criticality, you can get, compared to the other approaches, some performance improvement, as you expect. And there's also this metric of unfairness that we mentioned that the batch thing tries to take care of. And what they're claiming here is, it also does fine in terms of fairness. We're not sacrificing that much fairness to get this extra performance, right? All right, so the second paper has a similar goal. It's a paper that looks at packet scheduling again, but it does it in a slightly different way. It's called iadegia. It's a Greek word. Actually, I'm from Greece, so this makes sense for me. This lazy cat was in the original presentation, so I left it in. Iadegia is the spirit of laziness in Greek mythology. And the idea of this paper is to expose this slack or laziness into the network. So when a packet gets injected into the network, you want to have some notion that tells you, how lazy can I be with this packet? Instead of saying how critical do I have to be. And the difference compared to stall time criticality is stall time criticality was on a per application basis ranking. So you didn't distinguish between individual packets for an application. You just said this application has higher criticality than another one. In this work, you can also distinguish between packets. So there are some packets that are more critical from the same, even from the same application, and some others that are not, right? So yeah, the whole paper is built around this notion of slack. And slack is how many extra cycles can I delay this packet without causing stalls. Again, memory level parallelism is the main source of this slack. So you have these overlapping memory requests, and some of them are sort of prefetch requests because you haven't reached the point where you're going to need it yet, but you already sent out the request, so it might be able to be serviced a little bit later. Let's look at an example. This just shows you the slack. You have an instruction window here on the left, and you have a green load miss that starts getting serviced. It just happened that in this case, the L2 slice that had to service this was all the way on the other side of the network. So you're going to traverse multiple hops to get there and get back. And then later on, you have a blue miss that is pretty close. Now, you will be stalled on the green one for quite some time because you have to go on the other end of the chip and bring it back, while the blue one is probably going to come back much faster. But it doesn't need to. And that's the important observation of this paper, is that there is stall time. There is slack for this blue packet. And the slack is essentially this distance here. Because It doesn't matter if the blue packet arrives here, here, or here. As long as it arrives, sometime before you're done with your stall, it should be the same. It won't make a difference from the core's perspective. And we'll see an example. In this case, there wasn't that much conflict between the two packets. Maybe a little bit at the end, they're sharing some links. But sometimes it's the case is that these not high priority packets are blocking higher priority ones. And that's a case where you want to make sure that you're picking the right packets to make progress. So this is the idea of the paper. This is the same scenario. You have this green critical request and this blue one that can afford some delay. And then let's say you have another core that has an orange request that is critical, and then an MLP request, a red one, that is not as critical. The problem that happens here is this red request that is not as critical happens to be using some of the same links as the green request from core A that is critical. Along these three routers, it might happen that these packets end up in neighboring buffers, and you just want to make sure that these routers make the right decision. They prioritize the green one, which is a critical packet, and the red one can arrive later. And in particular, if you want to do that in a fine-grained manner, you don't want to just say green is always higher priority than the red one. You want to say the red packets can be delayed by this many cycles. For instance, by 6 cycles in this case, by 6 hops. So if you're over 6 hops, well then you do want to also prioritize the red one, because at that point you might be needing the red ones. So the priority does change dynamically, or can change dynamically as time goes by. Yeah, so this just says what I said. The slack of the red one is bigger than the slack of the green one. So you're going to prioritize the one with the least slack, the one that has to get to its destination immediately. So this paper characterized some, I think, spec benchmarks with respect to how much slack their packets have. This is one example, GEMS, and this is the percentage of packets. So less than 10% were critical, like they didn't have any slack. You had to get these back. And then you have different amounts of packets, like about 50% of packets had 350 cycles tolerance and latency. That wouldn't change the outcome of the computation, of the timing. So this way you can sort of see, there's some critical, some non-critical packets, and different applications have very different behavior. This is another benchmark, and this one has a lot of critical packets. So this means it's probably it might be a low MLP application, so it really needs the data back as soon as possible. And then you have everything in between, so it's not a one solution fits all kind of problem. You need a tailor to the specific application. Okay, you can look at the paper for how slack is computed, but keep this in mind. If you're sending a packet, you don't necessarily know how much slack you should assign to that packet. You don't know beforehand because you don't know how much stall time you're going to have beforehand. So you need to predict that. And this paper has some mechanisms for predicting that. For instance, one predictor can be the number of hops I'm doing. So if I send a packet A, that I know is going to end up going to the other end of the chip, I know that the next packet I'm going to send is probably going to have some slack, because the first packet is going to take so long to get back, and this has so many hops that I'll have some tolerance with the next packets. So that's one of the metrics. You can also look at the history of your previous packets and see usually my packets had this much slack, so the next ones probably will have similar slack. And look at the paper to see the exact mechanisms, and there's some interesting heuristics there that you can do. This is a slack estimation algorithm, and essentially it does sort of it looks at a few things. One of them is the hop estimate. So how many hops away do I think this packet is going to go? Is this an L2 miss? What kind of miss is this? Because depending on the type of miss, you have an approximation for how long it's going to take. Okay. And again, we have the problem of starvation, as before, right? So I don't want some of the packets to always be considered less critical than others. And the solution is kind of similar again. You do some sort of batching to make sure that everyone at some point makes progress. Okay. And they did a comparison against some previous techniques, among them GSF and the shortest job first. The shortest job first just says the guys that have the least amount of load, the quickest request, I'll service them always ahead of the other ones. So there are some combinations there. The best performing one is a combination of shortest job first with the IRGIA scheme, which captures the slack. So you get some improvements in system performance. I think there's also a fairness results in the paper, so you can take a look at that. Now let's see how much time we have left. Okay, so I think I'll briefly talk about bufferless. We have about 5 minutes left. So bufferless networks is, when we were saying before, what do you do when you have conflicts? You have two packets trying to use the same link. One of the options was to misroute the packet to some other destination. And that's exactly what bufferless does. So this from the original presentation. Let's first see why would I want to do bufferless. What's the problem with buffers? Well, the main problem is power. A lot of the energy in networks on chip does go to buffering. And this paper mostly focused on the energy savings. Now, keep in mind, all of these papers are biased, as Oner mentioned. What's come out from this group and most of his collaborations. And we have some other papers as well posted on the site. So also take a look at those, to get a more balanced view of what's going on in networks on chip. So bufferless is an interesting domain, but there's also other ideas of how to split buffers and what other optimizations to do. But this is one proposal. And I think back, when this paper was written, there was these two examples that showed a pretty big, percentage of your power being spent on the network on chip, in the buffers on the network on chip. They say there's a lot of work done. Most of them, though, look at buffered approaches. And in this work, they don't want to assume buffers. So this big portion of each router is dedicated to buffers. And this paper suggests that we drop this. So you have these buffers because if you have a conflict, let's say both of these red ones want to go through output channel 1, only one can make progress. We need the buffer to store the other one. What if we didn't have buffers? What would we do then? What would happen with that red packet? And you'll see in a couple of slides. Before I go further, actually this I wanted to mention, the load latency, but I forgot. Remember this curve we saw? This was the load latency behavior of a network, and it typically looks sort of like this. If you add buffering to a network, you usually shift this curve to the right or to the left. If you add more buffering, it gets shifted to the right, so you have a higher saturation throughput. If it gets shifted to the left, you have a lower saturation throughput. I think the original presentation was timed, and it has the hints in it. So this is a general comment. Just keep in mind that more buffering usually exposes more flexibility to the schedulers, so they can use the network more efficiently. And as we said, there is a hard limit. At some point, the mesh that we saw can't go beyond 4 gigabits per second, but you can get closer to that by increasing the amount of buffering or the number of virtual channels you have.
So doesn't the larger buffers impact latencies at the lower injection rates?
No, it does not. So the buffers does not mean more pipeline stages, because when I go in a buffer, as you saw here, I don't have to go through each one of these entries. This is a FIFO. I go directly to the front. So this only, if you have a lot of packets being accumulated, then the latency will get higher, but if I'm idle, I can jump straight to the beginning. So the idle part here is not affected. Now, you might ask, why is this not higher already here? Well, it is because if this guy had, let's say, 8 buffer entries, and this guy had 16, up to 8 buffer entries, they're going to behave the same. Once you start using more than those 8 buffer entries, this guy will already have shot up because his 9th buffer entry didn't even exist, so the previous guy is going to already be overloaded. This guy might be able to sustain some more throughput before he reaches that critical point. Okay. So essentially this says, buffers, yes, we need them if we want networks to perform very well. Now the question is, and the downside is they consume large amounts of energy, power, and they also add some complexity because you have to manage them and you need to pick which one you're going to queue into and which one you're going to dequeue from, and area, which I guess again correlates with the energy. But if I don't need that much performance, do I really need to have buffers in my network? And this paper argues that for the benchmarks, for the workloads that typical CMPs run, you don't really need that aggressive of a router design. So that shows you kind of what kind of difference you can expect. Without any buffers, you're really going to get shifted to the left. So you're going to have much less bandwidth than what you would have with buffers. But the question is, do we really need it? And what do I do with those packets that I don't have a place to store them? So this looks at a few different variants of a scheme called BLESS, which is for bufferless routing. And let's look at the idea here. This goes back to this hot potato routing idea. The routers don't store the packets, they want to get rid of them. So in the buffered case, you have two packets coming in, they want to use the same output link, one of them gets stored, the other one gets forwarded. In the bufferless, both of them want to go up, but one of them gets deflected and it gets shot in some other direction than the one it really wanted to go towards, right? And I think Owen already covered this. So we get rid of the buffers. We also get rid of some of those other control logic things because now we don't need a deal about which VC we're going to use or which routing output we're going to use, because if I can't make it towards the productive one, I just go towards another direction. All right, this is time. To make sure that you're making progress, you need to have some sort of ranking between flits, because if I'm a really unlucky flit and I keep on getting deflected, I'll never make it to my destination. And that makes this paper kind of tricky. And there have been some follow-up work that looks at how you can minimize this chaos under high loads. Because if you start having many conflicts, there's going to be a lot of packets just circling the network. And the problem is with the worst case scenario. Under realistic or common loads, it might work fine, but the worst case can get pretty bad. And not only that, but think of this. If you start having many flits that are just circling, going around in the network, it might happen that many of those flits all need to go to the same destination. And that means there's a poor guy in the network that might suddenly get tons of packets that were all inside the network, and he needs to be ready to have enough buffer space to drain all those packets out of the network. So there's some, work that's been done on top of this to reduce, for instance, the amount of buffering required at the receiving endpoints. And I think we're almost out of time. Let me just go, I guess, to the next slide that shows just a few of the results, just so you can see what this looks like. This we've covered. This technique also does what you mentioned. It cuts packets, and it can create a new worm out of an existing one, two smaller worms. And this is the algorithm they use. They can truncate, which is the cutting of the worms. And let's go just straight to the results. Also, as we mentioned, your pipeline latency can get reduced. Your pipeline stages can get fewer. And let's see, this is the evaluation. Here we go. All right. So at a first glimpse, things look bad, because with all the bufferless variants, you saturate much earlier at about 20% injection rate. With a buffered one, you can almost reach 50% injection load and still have good throughput. So it looks kind of bad, but what happens is in most applications, you usually operate in this region. So that's still fine. You don't ever need to go at such high loads. This is the way to speed up for some applications. And actually, let me I want to jump to this graph here. So this is the big benefit is this power savings. And this shows here the red portion is the energy spent on buffering. And that's where you get a very big reduction by eliminating all those buffers. And then if you look, we got this big savings in buffering energy, and our performance remained pretty good. There's some small degradation, but it's pretty good relative to the energy savings we got. So that's a takeaway, of this paper. Big energy savings, small degradation in performance. And that concludes the lecture. So do you have any other questions?
Regarding virtual channels, does that mean that it has to be that you just have one packet per channel?
For virtual channels, once again the question?
Just one packet per channel? Is that how it works?
No. When you say one packet, do you mean that the buffer can fit one packet?
Can you mix up packets in a single virtual channel?
Yes, and when you say you can mix multiple packets, so the virtual channel, let me go back to that. I think this is important to understand. Sorry, I think there's a faster way to go back. Let's see. Here, this should be good. There. So each one of these buffers corresponds to a different virtual channel. In here, in this virtual channel, I can get more than one packet, and they can even be destined to different outputs or the same output. The VC is sort of a virtual tag on the packet. You can assign it any way you want. If you want, you could have all your request packets on VC0 and all your response packets on VC1. The network doesn't necessarily have to impose your VC assignment. Or if you want, you can have the network assign different VCs. Now there's some more subtle there's some subtleties with assigning VCs and which VCs get exposed to the clients. So if I'm sending a request as a client, do I mark that I want it to be on VC0 or VC1, or does the router take care of that? What happens there is you can have what we usually call message classes, and that is exposed to the clients. So if I'm a core and I'm sending a request, I can tag it as a request. And then you have virtual channels, which is just the different buffers in here. And you can have a router that, for instance, takes message class 1, which might be the requests, and only uses the top 2 VCs for those, and message class 2, which might be responses, and only uses the bottom 2 VCs for those. So the way you use these buffers is can be independent from the contents of the packet. So you can mix different packets. I could mix requests and responses here. I probably wouldn't want to because I might run into deadlock issues, but there's nothing preventing me from having more than one in different packets here. One last note on that. There's a scheme called virtual output queuing. And in that particular router organization, I need to have as many VCs, at least as many as my outputs. And then as my packets come in, I look at which output those packets are going to use, and I use the corresponding VC. So in that case, VC, I guess 0 or 1, will only have packets destined to output 0. VC2, only packets destined to output 2, and so forth. In that case, I have complete isolation. I don't have any head of light and I'm blocking. Because I only have packets to 1 here, I only have packets to 2 here, packets going to 3, to 4. So I can never have something be stuck behind something else. That's sort of one way of using your VCs. But the VCs are kind of oblivious. This is whatever info the router gets from the previous router, he will blindly use and put it in that VC. So if I said use VC3, he takes the packet, writes it there. This router, in the VC allocation stage, can make a decision as to which VC he's going to use downstream. But that doesn't necessarily have to be made by the router. You could have the clients enforce VC restrictions. Is that clear? Yeah? Okay. Any other questions? All right. So don't forget your paper reviews and milestones on November 6th.